Okay, guys, just a couple of reminders here before we start the notes, a couple of announcements. This is just a reminder that we do have a mini quiz coming up this Friday. The Delta Math practice for that mini quiz has been pushed out to you guys yesterday. So if y'all haven't had a chance to start working on the Delta Math, please go ahead and make sure that you start working on it. The due date for the Delta Math is set for Friday at 11:59 p.m. But again, it's to prepare you for the mini quiz that you're going to take in class on Friday. So try to have that Delta Math done, if possible, Thursday night at the latest. Okay, so just jumping into the notes, we're looking at chapter 5 today. We're looking at the first day of notes, which will be going over bisectors of triangles. These first 2 days of notes are going to be covering some special segments of triangles. And the first two special segments we're going to be focusing on today is going to be our bisectors. So to start off, the very first special segment we're going to look at is a perpendicular bisector. So a perpendicular bisector, this can be a line, a segment, or a ray that is perpendicular to another segment and intersects that segment at its midpoint. And this is where you're going to kind of want to use context clues here. We understand what the word bisect means, right? A bisector means that we're going to cut something in half, right? So what a perpendicular bisector does is it cuts a line segment in half. And what's special about this bisector is that it's perpendicular. So it's in the name, okay? A perpendicular bisector is going to cut a segment into two congruent pieces. And it's going to do it in such a way that it is perpendicular, meaning that it's going to create a 90-degree angle. So as we look at the picture here, that's kind of what the focus is. As I look at this diagram over here, line QS represents our perpendicular bisector. We see that what is being bisected is this bottom side right here, PR. It's being bisected and cut into two congruent pieces, where this piece, PS, is congruent to SR. And not only is it bisecting it, it's bisecting it in such a way that it is perpendicular, hence the 90-degree angle that's formed there. So that's a perpendicular bisector. Now, we have something here known as the perpendicular bisector theorem. So the perpendicular bisector theorem states that if a point lies, and I'm going to highlight the important parts here, if a point lies on the perpendicular bisector of a segment, then that point is equidistant to both segments' endpoints. And so that's what we're going to really focus on here. And one thing to make note of here is that the converse of this statement is also true. So that was kind of a lot to read. Let's just kind of go over that again. So this says, and I'm going to walk through it on the picture so that this makes sense. So look at the diagram here. It says if a point lies on the perpendicular bisector. Looking at this picture, line CM is my perpendicular bisector. If this point C lies on the perpendicular bisector, it's understood that that point is going to be equal distance to the endpoints of that segment that just got chopped in half, meaning that these two segments are going to be congruent. That's what the perpendicular bisector theorem is stating. And the converse of this statement would be true. Okay, if you see that we have a point that is equidistant to both segments' endpoints, then that means that the point must lie on the perpendicular bisector. And we'll see some examples of what this looks like so that you can see what this looks like in action. The next kind of vocabulary term that we want to go over is equidistant. It sounds exactly what, or it's going to be exactly what it sounds like here. Equal distance. Equidistance literally just means equal distance. So the same or equal distance. Away from something. So in the example that you have in the diagram here, it's noted that this point Q is equidistant to P and to R, which is indicated here by these two tick marks. Q is equidistant to P and R. Okay, so equidistance, kind of just sounds the exact same. And so here's where we get into a new vocabulary word here known as concurrency. Okay. Concurrency is defined as whenever we have three or more lines, segments, or rays that intersect at one point, and we call their intersection the point of concurrency. Okay, so your point of concurrency, at least for the notes that we're looking at in this chapter, your point of concurrency is where these special segments intersect. So for example, we have perpendicular bisectors. If I'm looking at triangles, which we'll be looking at a lot today, we'll have three perpendicular bisectors. Where those three perpendicular bisectors intersect is known as the point of concurrency, which we'll see pop up later in the notes. But for right now, let's go ahead and start looking at some examples of some of the items that we've just looked at. So example 1 says, in the diagram, MK is the perpendicular bisector of NL. So I can't really highlight a whole lot. I'm going to be marking things on the picture and then erasing just so it doesn't get super cluttered. So MK, this blue line right here, happens to be the perpendicular bisector of NL. Okay, so what's happening right here is that this line segment NL is being cut in half, meaning that these two pieces are congruent. And they give me some given information there. But if I start with part A, it says list all congruent segments. Well, we know that MK is bisecting NL, so it's understood that NY must be congruent to line segment YL. In addition to that, what we're also seeing here is that what we'll see is this point K happens to be on the perpendicular bisector. And what we saw earlier right here was known as the perpendicular bisector theorem. If I have a point on the perpendicular bisector, then it's going to be equidistant to both endpoints. So if I look here, this is implying that NK and LK are going to be congruent. In other words, that the distance from this point to that endpoint will be the same as the distance from K to the endpoint L. So those will be congruent. And that is known as the perpendicular bisector theorem. So we can also mark down here that NK would be congruent to LK. And we also have that popping up on the other side as well. So if I take a look at the other side, what you'll notice is that point M also happens to be on the perpendicular bisector for this diagram. So that would indicate that M is equidistant to N as it is to L. And we'll do this with 3 tick marks so that we don't get those confused. So last congruent segment that I can really make here is to state that MN is congruent to ML. So that represents all of our congruent segments, okay? And so like I said earlier, I'm going to go ahead and go through these problems here, and I'm going to erase as we go so that it does not become super cluttered. So we're just going to erase this here. And we'll go ahead and continue with answering part B here. So if we take a look at part B, it wants us to find NK. So in the diagram, I'm going to label what is marked here, okay? We know that MK is the perpendicular bisector, so I know these two pieces will be congruent. It says YN is 8, and YL is the same as YN, so this is also 8. They also labeled that NK, which I'm purposely doing this in the same color as I used earlier. NK is 6x minus 5, and LK is 4x plus 1. And recall from earlier that because K is on the perpendicular bisector, then that must mean that these two pieces have to be congruent. Well, if those two pieces are congruent, then what we can go ahead and do is solve for x. I'm solving for x here because they're asking me to find NK. Well, I'll know NK once I know the value of x. So our focus is there. So if we're saying here that NK is congruent to LK, then we can write the following equation that 6x minus 5 is equal to 4x plus 1. My focus here is really on the setup and getting you guys to see these new theorems. When we get to the solving piece, I'm going to try to go through this quickly so that y'all aren't sitting there miserable for 30 minutes watching this video. So I'd subtract 4x on both sides to get 2x minus 5 is equal to 1. We would add 5 to both sides, giving you 2x is equal to 6. If I divide by 2, we get that x is equal to 3. Now, NK is represented as 6x minus 5. So if x is 3, 6 times 3 minus 5, well, 6 times 3 is 18. Subtract 5, we get that NK is equal to 13. So NK is equal to 13. So we can fill that in right here. The question here is also asking for YK. So if I'm looking for YK, let's fill in the picture what we already know. We know that this is 13. And because nk is congruent to lk, this must mean that this is also 13. What the question here is asking now is they want to know the value of yk. So yk is right here. Okay. One thing that I didn't mark earlier is this information listed right here. Let me change colors. They mentioned that mk is the perpendicular bisector of NL. So mk, if it's perpendicular, that means that a right angle is formed. Right angles formed here, right angles formed here, here, and here. 4 right angles have been formed. The question here is asking you for yk. So what I'm working with here, it's not letting me highlight, but I'll do my best to outline it here. What I'm working with here essentially is yk is what I want to find. I'm working with this. We can work with this top triangle, honestly, here. That top right triangle, what I'm going to do is I'm going to pull it out and draw it off to the side. So this is y and k. We already know that from y to n is 8. We found out that nk is 13. We got a right angle here. What we need to find out is what yk is. If I don't know what yk is, we can actually just call it, well, let's not call it x. Let's call it y, just so that we're using a different letter. And one thing that you should have learned in middle school is the Pythagorean theorem. If you know two sides of a right triangle, you can find the third side using Pythagorean theorem. Pythagorean theorem is a squared plus b squared is equal to c squared, where your c is the hypotenuse. So that's my c. My a and b will be 8 and y. So as I plug these values in, a squared plus b squared equals c squared is going to give us 8 squared plus y squared is equal to 13 squared. 8 squared is 64, plus y squared is equal to 13 squared, which gives us 169. If I subtract 64 on both sides, what we end up with, let me write it off to the side here, we get y squared is equal to, well, 169 minus 64 is 105. And if I want to find the value of y here, what we're going to do is cancel out that cancel out that squared by square rooting. So we get the square root of 105. And normally what we do here is check to see if that simplifies. And you can do so by just breaking that off to the side here. I know that this is divisible by 5. This will be 5 times 21. 5 is prime. 21 breaks down into 3 and 7. You'll notice that I don't have any pairs of the same number. So this 105 is actually in simplest form. It cannot be simplified. So our y in the picture here is square root of 105. And y is what we labeled for yk. So yk is the square root of 105. Okay, so that's the perpendicular bisector theorem there in action, and then us using Pythagorean theorem there to help us find some missing information. So with that being said, let's go ahead and keep moving. Example 2 says ZS is the perpendicular bisector of WT. Find the values of x and y. So if ZS is the perpendicular bisector, and one thing we were going to want to get in the habit of doing that I should have done in the last problem is label everything that it means to be a perpendicular bisector. So if ZS is the perpendicular bisector, that means a right angle is formed here and here. That also means that WT is the object that actually got bisected or cut in half, meaning that y plus 5 must be congruent to 3x minus 5. Similarly here, it's also understood that because point Z is on the perpendicular bisector, that point Z must be equidistant to W and to T by the perpendicular bisector theorem. So we're asked to find the values of x and y. I can set up an equation there with my sides that are congruent that are marked in green. We can say here that 9x minus 13 is equal to 2y plus 16. And now if you look at that equation, it's got an x and a y. Okay, so that's already a red flag. I can't solve it. So typically this is an indicator that you're working with the systems of equations. So I'm going to look at these sides right here. Those sides are congruent, so I can make an equation that says they're congruent. So we can set up the equation 3x minus 5 is equal to y plus 5. So what we're working with here is very clearly a system of equations. To solve a system of equations, you've got three options. You can solve by graphing, substitution, or elimination. I like to do elimination because you can avoid fractions that way. So what I'm going to do is I'm going to get this geared up for elimination. Just a quick review on how we solve by using elimination. You want both your equations to be in this form. Ax plus by is equal to c. So that's going to be my objective here. What I'm going to do here is I'm going to get the green equation with the x and the y's on the left and the constants on the right. So I'm going to subtract 2y on both sides. That would give us 9x minus 2y minus 13 is equal to 16. From here, got to move that 13 over, so plus 13. We get 9x minus 2y is equal to 16 plus 13 is 29. So there's one equation set up for elimination. I'm going to take that blue equation and pretty much do the same thing. I'm going to get the x's and y's on the left, constants on the right. So I'm going to subtract y on both sides. We get 3x minus y minus 5 is equal to 5. From here, move that negative 5 over, so plus 5 on both sides. We're left with 3x minus y is equal to 5 plus 5 gives us 10. So here are my two equations geared up and set up for elimination. What I'm going to do now is I'm going to stack these. So I got 9x minus 2y is equal to 29, and I got 3x minus y is equal to 10. Well, the way I like to do systems is I like to add vertically. So the goal here is for something to cancel out. If I add vertically, nothing immediately cancels. So what we're going to do here is we're going to manipulate one of these equations, or sometimes you have to manipulate both. In this case, what I'm going to choose to cancel out is I want to cancel out this negative 2y. To cancel out a negative 2y, I need a plus 2y. So I'm going to multiply this by negative 2. If I multiply this bottom equation by negative 2, what that ends up giving us here is negative 2 times 3x is negative 6x. Negative 2 times negative y, well, a negative times a negative makes a positive, so plus 2y. And then negative 2 times 10 is negative 20. What I'm going to do now is just simply rewrite that top equation. So 9x minus 2y is equal to 29. And now when we add vertically for the systems, you'll see that the y's end up canceling out. And we're left with negative 6x plus 9x. Well, that gives me 3x. And then negative 20 plus 29, that gives me positive 9. Now when I divide by 3, we see that x is equal to 3. The question asks you to find the values of x and y. We found x, just got to find y. So if I want to find y, all that's left for us to do is plug it into one of those original equations, or any of those equations that you manipulated, honestly. What I'm going to choose here, just because I got space for it off to the left, I'm going to plug it into this equation right here. We know that x is 3, so plug it in. 9 times 3 minus 2y is equal to 29. Well, 9 times 3 is 27, minus 2y is equal to 29. If I subtract 27 on both sides, what we're left with is negative 2y is equal to 29 minus 27 is 2. If I divide by negative 2 on both sides, then y is equal to 2 divided by negative 2 gives us negative 1. So y is equal to negative 1. Right, that'll look clear. Okay, and so there is going to represent our values for x and y for this particular systems. Okay, so systems can be a little bit messy. Kind of does require a lot of work, but by now, hopefully, you guys are a little bit more comfortable solving these systems. So let's go ahead and keep it running here in the notes. The next thing that we're going to look at is circumcenter. So circumcenter happens to be one of the points of concurrency that we're going to look at in this chapter. So let me just erase this so it's not in the way here. Let's talk about what your circumcenter is. So your circumcenter is going to be the point of concurrency of the three perpendicular bisectors of a triangle. And this is called the circumcenter. So what I'm going to have you guys highlight here is something super important, okay? Point of concurrency of three perpendicular bisectors of a triangle is called the circumcenter. Okay. Okay, I guess it's not meant to be. It doesn't want to let me highlight it. So y'all go ahead and just highlight the word circumcenter. But just to kind of recall, because I know this is a lot of vocabulary being thrown your way right now. Remember that point of concurrency is going to be that point where three special segments intersect. Your special segments that are intersecting here are your perpendicular bisectors. So The point where all three perpendicular bisectors of a triangle intersect is known as your circumcenter. And we have three different scenarios on the location for this circumcenter. If I'm looking at an acute triangle, what I want you guys doing right now is I want you drawing in the perpendicular bisectors of each side for this orange triangle. So perpendicular bisectors means I'm bisecting each side and it's going to be perpendicular. So if I'm bisecting this side, it's got to be right in the middle, right? So my perpendicular bisector would look something like this, where it forms a 90-degree angle. My perpendicular bisector for this side here, okay, to the best of my ability here, I'm not perfect, but would look something like this. There's my perpendicular bisector. I cut that side in half. And then lastly, my perpendicular bisector for this third side would be about right here in the middle. So you'll notice here that your point of concurrency, let me do this in a different color here. Let me just do this in, I guess, pink. This is your point of concurrency. So if the triangle is acute, what you'll realize is that your circumcenter is going to be located inside the triangle. So be located inside the triangle if it's an acute triangle. Okay, the next scenario we have is, well, where is this going to be located if I have a right triangle? Well, you can already tell by looking at the black dot, it's going to be located not inside, not outside the triangle, but on the triangle. And here's where we're going to draw in these perpendicular bisectors. So here's one perpendicular bisector. Here is a second one. And then here is your third one. Okay, so what you'll realize here is that your circumcenter, that point of concurrency where all three perpendicular bisectors intersect, happens to be on the triangle whenever we're looking at a right triangle. So if it's a right triangle, it's on the triangle. If it's acute, it's inside. And you can guess for obtuse where it's going to be located. If I look at the obtuse triangle, let's draw in those perpendicular bisectors. So here's one of them, and I'm going to kind of just do my best to draw this so that it's perpendicular. There's one perpendicular bisector. Here is another. This is about in the middle here. Here's another perpendicular bisector. And then lastly, look at this one here in red. Here's a third perpendicular bisector, which if I go this way, I just have to extend it. So what you'll see is that your circumcenter, that point of concurrency where all three perpendicular bisectors intersect in an obtuse triangle, happens to be located outside the triangle. Okay, so again, kind of a lot of vocabulary to remember here, but please just remember that your three perpendicular bisectors, where those intersect, we call that the circumcenter. And something else worth mentioning here is, please remember that distance, anytime we're looking at distance from a point to a line, it must be perpendicular. It's got to be perpendicular. Okay, so anytime we're looking at distance, we're always looking at perpendicular here. Okay, so we talked about perpendicular bisectors. Now let's just go in detail about angle bisectors. So perpendicular bisectors cut line segments in half, and angle bisectors in the name. It's going to cut an angle in half. So as we're looking at an angle bisector, what you're putting in the blank here is an angle bisector can be a ray, can be a line, or a segment. And what this angle bisector, this ray, line, or segment does is it splits an angle into two congruent angles. All right, and so that's your angle bisector. Okay, I'm highlighting this just because this is an important vocabulary term that you should be familiar with here. And so what we're going to look at now is a diagram of what this looks like. If I take a look here at an angle bisector, in this particular picture, I'm just going to label this here that AD is the angle bisector of angle BAC. Okay, And we have something very special that happens that is known as the angle bisector theorem. So the angle bisector theorem says that if a point lies on the angle bisector of an angle, then that point is equidistant to both sides of the angle. Okay, and then similar, like we said earlier, for perpendicular bisector theorem, the converse is also true. Okay, so it's very, very similar actually to that perpendicular bisector theorem. So if a point lies on the angle bisector, then that point is equidistant. Not gonna let me highlight here, but we'll run with it. It'll be equidistant to both sides of the angle. All right, and so that's what's being depicted here. Look at point D. Point D is on the angle bisector. And so we're saying that that point will need to be equidistant to the sides of the angle. This is my sides of my angle, okay? So it's going to be equidistant to those sides. I like to think about these types of problems. When you see this picture, it's going to be very unique. To me personally, I feel like this kind of looks like a baseball field. This right here kind of looks like first base. This looks like second base. This looks like third base. So when you see these baseball field type problems, please understand that it's going to be equal distance to both sides of the angle here, because they're not always going to mark that for you. Sometimes that's going to be left up for you to decide and remember. Okay, so that's our angle bisector theorem. So just like when we looked at earlier, we looked at circumcenter. Remember, circumcenter is where your three perpendicular bisectors intersect. We have another point of concurrency called the incenter, and this will be where all three angle bisectors intersect. So the point of concurrency of the three angle bisectors of a triangle, we call that the incenter. And one thing to make note of is that the incenter is equidistant from the three sides of the triangle. So thing to remember here is point of concurrency of three angle bisectors, we call that the incenter. So just pretend like you can highlight there. It's probably going to disappear for me. So, and one thing to also make note of here is the location of the incenter. Incenter always going to be located inside the triangle. Okay. So this diagram's a little hard to look at. I'm going to zoom in as much as I possibly can here, but what I want you guys to notice is you're basically looking at two segments here. So looking at the blue lines here, okay, let's focus on the blue lines. This blue line is an angle bisector. This blue line is an angle bisector, and this blue line is an angle bisector. We just said that the point where those three angle bisectors meet is called the incenter. What you need to know about the incenter is that the incenter is equal distance to each side, meaning that these little red line segments here would have to be congruent. So to give you an example here for context, if this was 4 units away, then it's 4 units away from each side. That's one of the special properties of an incenter. And so what we'll look at is a few examples here, and then we'll wrap things up. So let's take a look at example 3. So it says if LO is equal to x squared minus 3x, NO is 30 plus 4x, find the value of x and NO. So this is kind of what I was telling you earlier. This kind of looks like a baseball field. So this is using the angle bisector theorem, which says that if I have a point, which is point O, if I have a point that is on the angle bisector, then that point is going to be equidistant to the sides of the angle, meaning that LO would have to be congruent to ON. And they happen to give us the expressions that represent LO and ON. So LO is x squared minus 3x. That is congruent to or equal to ON, which they just said is NO. So it's going to be equal to 30 plus 4x. So what this problem is looking like is factoring, okay? Factoring, we'll run through this really quickly here. To solve by factoring, you need this equation equal to 0. So I'm going to move the 4x over, and I'm going to go ahead and move the 30 over as well. That cancels, and we're left with x squared. I'm looking at negative 3x minus 4x gives me negative 7x, and then we have minus 30. That is going to be equal to 0 now. So what I'm looking at is when you're factoring with no number in front of x squared, you're simply just looking at what numbers multiply to give me negative 30 and add to give me negative 7. Okay, numbers we're working with here are going to be negative 10 and positive 3. So x minus 10, x plus 3. When you factor and you're asked to solve, you're going to set each factor equal to 0. So if x minus 10 is equal to 0 and x plus 3 is equal to 0, we're going to get the following solutions: that x is equal to 10 and x is equal to negative 3. Now, question said, find the value of x. How do I know which one is the value of x here? Well, you have to plug both in. There's a chance that one of them works and the other one doesn't. So first thing I would check for is I would plug in 10. Okay. Ideally, you would plug into both of them. I'm just going to plug in here. Let's actually do it for both, actually. So if I get 10 squared minus 3 times 10, well, 10 squared is 100, minus 30 gives me 70. That checks out. That's valid. If I plug that in for NO, though, we get 30 plus 4 times 10, which gives us 30 plus 40, which is 70. Okay, checks out. So x equals 10 seems to be a valid solution. So that works. We test now x equals negative 3. So test out here that x equals negative 3. Well, I guess let me leave that there. If I want to test out when x equals negative 3, then I have negative 3 squared minus 3 times negative 3. That is for LO. Well, negative 3 squared is positive 9. Minus 3 times negative 3 is negative 9. Minus a negative turns into a plus. So 9 plus 9, 18. So LO equals 18. NO is equal to 30 plus 4 times x. Well, we're testing negative 3 right now, so 4 times negative 3. So NO would be equal to 30. 4 times negative 3 is negative 12, so 30 minus 12 gives us a value of NO to be 18. So both of these solutions actually check out. And if I read the question, it says find the value of x. Well, my values of x, both of them work, so I'm going to circle both of them. X can equal 10 and x can equal negative 3. Now my values for NO, well, NO can be 18 like we just found. Or if I plugged in the 10, NO could also be 70. Okay, so my answers here, again, you can have two possible correct values. Your job is whenever you factor and solve, please make sure that you are testing both. All right, let's go ahead and keep it going here. If I take a look at example 4, example 4 has this picture here, okay? And one thing I want you guys to notice here is that these little segments here in blue, they are representing the distance from that point N to each side. And if they're marked with the right angle here, what's implied here is that those red lines right there, this is an angle bisector. This is an angle bisector. This is an angle bisector. So that green dot right there represents your incenter. And one of the properties of an incenter is that we said that the incenter is equidistant to each side. So that means that if that's 14x, this is 14x in blue. And NH would be 14x. What this question is asking you is find the value of x if point N is the incenter. So that's what I get for reading. I always tell you guys to read, and I just fell victim to not reading. The reason why I know that the red lines are angle bisectors is because they said N is the incenter. Okay, so main takeaway here is please remember incenter is going to be equidistant to each side. So what I'm working with here is that triangle that I erased in the beginning. Okay, what I'm going to focus my attention on, it doesn't let me highlight, so let me just color this in a different color here. Let me do this in, I guess, yellow. I'm going to focus my attention on this yellow triangle right here. Okay, if I have a right angle there just outside that triangle that's in yellow, it forms a linear pair, so this right here would be a right angle as well. Okay, I'm just going to erase it there so it's not blocking our 14x. So what I'm doing here is I'm separating out that yellow triangle. So right angle right here. This is 14x, this is 24, and this is 25. So what we're looking at again here is Pythagorean theorem. Okay, so Pythagorean theorem, remember we're looking at a squared plus b squared equals c squared, where c squared is your hypotenuse, which the hypotenuse is always across the 90. So that's c. Then these two sides can be a and b. Doesn't matter if you make the 24 your a value, it works out all the same. What does matter is that c is your hypotenuse. So as we start plugging these values in, my a is 14x. So I got 14x. I'm squaring that, so put the entire thing in parentheses. Then we have b squared, so this is 24 squared, is equal to c squared, which is 25 squared. Here's where things get a little bit tricky. A while back, we did a mini quiz that talked about properties of exponents. Whenever you're squaring an expression like this, you square everything inside. So if I were to square everything inside, we're doing 14 squared, which 14 squared is 196, and x squared, well, that's just x squared. Then we have 24 squared. 24 squared, if you need to check with the calculator, it is 576. And that's equal to 25 squared, which is 625. So from here, we're just solving for x. So my goal here is to get the x by itself. So I'm going to move the 576 over. If we do that, we get 196 is equal to, well, 625 minus 576. I lost my x squared there. 625 minus 576 is going to be 49. And then if we end up dividing both sides by 196, then what we're left with here is x squared is equal to 49 over 196. And I'm going to show you guys something very special that happens whenever you're square rooting a fraction here. So 49 over 196. If I want to solve for x, I need to cancel out the exponent of 2. So we're going to square root both sides. Now, when you square root a fraction, what that essentially is doing is you're going to square root the top and you're going to square root the bottom. So x is equal to the square root of 49 over the square root of 196. Well, what is the square root of 49? It's 7. And the square root of 196, square root of 196 is 14. So x is equal to 7 over 14. And if we simplify that, I can divide the top and bottom by 7. We get x is equal to 1/2. So my value of x here for this particular problem is x is equal to 1/2. And these are kind of those more challenging questions that we're trying to push you guys to become more comfortable with. Let's go ahead and wrap things up here with example 5. So it says, if n is the incenter of triangle JGH, the measure of angle NGM is 35, the measure of angle MNH is 69 degrees. What is the measure of angle KJN? So they were nice enough to pretty much label those angle measures in the picture for us. Let's take a look at what they're asking you to find. Asking you to find angle KJN. KJN, they're asking you for this angle right here. This angle right here in green. That's what they want to know. So let me just mark it there. So kind of some important vocabulary that they tell you here is they tell you n is the incenter. Okay, the incenter, remember this is the point where all three angle bisectors intersect. So this is indirectly telling us that we got 3 angle bisectors drawn in here. So our attention shifts to that here, okay? If I look at this problem, okay, I'm looking for angle KJN. So my focus here is I'm looking at angles. I'm not looking at the blue side, not the blue sides, but I'm not looking at the blue segments because that just tells me that the blue segments are equal distance to each side. Side lengths do not help me with angles here in this scenario. So my focus is I want to find the measure of an angle. Let's focus on the angles. So because I'm looking at an incenter is the point where all 3 angle bisectors intersect. That means that this right here is an angle bisector. So that means that if that's 35, this is 35. Right, that's what it means to be an angle bisector. Those 2 angles are congruent. Similarly, over here, if this is an angle bisector, and this is an angle bisector, right? The only issue is I don't know what that angle is, but I can find that angle because if I take a look here, I have a right triangle that will allow me to find that third missing angle. So if we do 69 plus 90 plus, let's call this guy x, that has to equal to 180, right? The 3 angles in a triangle add up to 180. 69 plus 90 is 159, plus x equals 180. If I subtract 159, then we see that x is equal to 21. So let's clean this up here. We are looking at this angle bisector right here. We just found that this guy is 21. So if that's 21, this is 21. And now we can start getting closer to how we're going to find the measure of angle KJN. KJN is an angle bisector It's created by an angle bisector and will be congruent to this angle right here. So now what we're looking at is this triangle as a whole. If I look here at this large triangle here, then let's look at the three angles I'm working with. That top angle, angle G, would be 35 plus 35, that's 70 degrees. Angle H would be 21 plus 21, that's 42 degrees. I need to find angle J, okay? Angle J, those three angles would add up to 180. So angle J plus 70 plus 42 would have to equal to 180. Well, 70 plus 42 is 112. That's equal to 180. When I subtract 112, what we end up with here is that angle J is equal to 68. So that angle J is equal to 68 degrees, but because that angle is being bisected, it's being split up into two congruent angles, so I'm going to divide by 2. That would mean that each half of that angle is going to measure 34. So this would be 34 degrees, this would be 34 degrees. So to answer that question, the measure of angle KJN is going to measure 34 degrees. Okay, so that's going to wrap it up for the notes here. What I would suggest here is practice with the homework that is going to be available on Class Notebook. If you're having trouble pulling up the homework, I know some people, the Class Notebook for some reason isn't receiving any of the homeworks that I push out. You can find the downloadable link of the Chapter 5 homework and notes on Canvas under the announcement sections. If you guys have any questions or concerns about the notes, test grades, anything like that, please feel free to send me a message in Canvas and I'll get back to you guys as soon as I can.